Hello and welcome to the webinar. Today we're going to talk about an open source app that we've been working on called Grow. Grow is an app that will track the growth stage of your plants throughout your farm. But before we really get into the app, I wanted to talk about the underlying concepts that it's built on, kind of just set the stage a little bit. But I'll mention that I'm an electrical engineer and a software engineer, and I know just enough about plant science to have built this app. Good thing is, on this webinar, we have some really great resources and people who actually know the plant science very well. So if you have any questions in this next few slides worth of material, we'll go ahead and we can ask them at the end of the talk and we'll get you a good answer. In the meantime, I'm going to do my best at trying to explain some of it. So we'll look at corn specifically, mainly because we're in Indiana and so it's a major crop here. But this general idea applies to a lot of different crops. And the app Grow can work for a lot of different crops. Right now it's sort of set to only work for corn, but we can add models for any type of plant that follows heat units like corn does. But we'll get into that in a little bit. Let's look just at the growth stages of corn. So just how do we classify it as it grows and it goes from seed to maturity? And there's sort of two major regions of corn growth: the vegetative stage and the reproductive stage. The vegetative stage is all about growing the plant itself. It's sort of just getting prepared for the reproductive stage. And we label the vegetative stage with a V, and then we also give it a sub-label of a number. So V1, V2, V3, so on, all the way up to roughly V20 or something like that. And the number describes how many fully emerged leaves are available on the plant. So you can see here that we have 1, 2, 3, 4, and 5 fully emerged leaves. You can tell that this leaf here is emerged because you can see its nodal ring right here. This leaf here and here are not fully emerged. The nodal ring is still below inside the stalk. It's still growing. At some point it'll fully emerge and we'll see it, and at that point the plant will move from V5 to V6. Right around the V6 stage, that growing point where these leaves are growing from has come above the ground level. And with every new leaf, at least up until V6, a new ring of roots emerge as well. And since that growing point is above the earth, the roots actually emerge above ground and come back down into the earth. We call these brace roots. So that's a pretty good indicator of V6 as well. And right around this same stage, where the plant starts producing buds for the ear and the tassel. And so really all the way as early as V6, the plant is working on building the reproductive parts, which are so key to increasing or having good yield. So all the way from V6 on, plant care is particularly critical in terms of maximizing the yield. The tassel grows on the top of the plant. It's the piece that carries the pollen. It's the last thing to grow. Once the plant gets to its full height, the tassel forms and the pollen prepares to fall, and we get to what we call VT, or the final stage of vegetative. At some point then the pollen falls and the silk has emerged, and we have moved from the vegetative phase to the reproductive phase. The first phase of the reproductive is silking. That's because the silk is emerged from the husk at that point. The silk is what accepts the pollen. There's one piece of silk going back to every kernel on the cob, and every silk needs to be fertilized if that kernel is going to form into a seed. So it's interesting to note that back here in this V6 to say V12 region, the plant is sort of deciding how many rows there'll be in the cob. But it's not until the R1 stage do we decide how full they are. What I mean by that is how many of the seeds will be fertilized to turn into an actual seed. And so there's sort of two really key moments in that affect yield: that that cob development phase from that V6 to V12, and then also that fill phase in R1. Once the pollination is complete, we move on to the blister phase where the seeds are beginning to form. There's sort of a clear sugary liquid. We get to the milk phase where that liquid becomes a little bit more milky white. This is where we harvest sweet corn. This is when we like the taste the best. A little bit early or a little bit late, the taste isn't so good. Then we have the dough stage in R4. Here the embryo for the new plant is starting to form. The milk is starting to solidify. We get to the dent stage next, so-called because a dent forms into the kernel tops like this. The embryo has become significantly larger. The seed is hardening still. And then finally we get to the maturity phase, or also known as the black layer phase. And that's because there's this layer right here of black that forms, and it becomes a barrier between the seed and the host plant, the parent plant. And at this point, the seed is fully grown. Nothing can really happen. Nutrients can't move across the black layer. And so it's ready for to be planted, to grow, or harvested for seed. Essentially, we're done. It's finished. And I'd say add a little shout out to Bob Nielsen for all these wonderful images and a lot of really great material on his website about all of this science. So you might be asking yourself, well, what's the point in terms of grower and grower procedures? And it turns out that plant care and farm logistics are really constrained by the growth of your crops. For example, to apply a herbicide or a fungicide, you have to do it at an appropriate growth stage. So for a certain product, there'll be a label that says you can only apply this below V3 or maybe above V6, worrying about damaging the plant, worrying about damaging the cob or the tassel, and so on. Like we mentioned before, the number of kernel rows is determined in that earlier V6 to V12 region. And also, similarly, the reproductive 1 phase being just as important. So soil and moisture, nutrient availability, stress management in those times are really critical to yield determination. So if you're going to do a good job managing care in that region, you need to know when you're in that region. And then finally, plants can be susceptible to certain diseases and pests at various growth stages. So if you know what growth stages to go out and check for a certain disease or pest, then you can treat that disease or pest in a timely manner, which will ultimately lower the stress and improve the yield. So to make all these decisions, you really do need to know what is the field state for all of your fields, really pretty much on a daily basis. But you might be asking, well, it's cool, but how do we practically apply this? Because I can't go field scout every one of my fields every day. We don't have the time to do that. So if I don't actually know what the different growth stages are, how can I actually apply that in practice to make better decisions? Well, one way to do it is to try to find a proxy that we can use, that we can more easily compute to estimate the growth stage. Turns out there's this thing called the growing degree day or growing degree units, GDU or GDD. And we'll talk about what they are in detail in a moment, but they're essentially computed from just daily temperature data. So pretty easily public and free data that you can find on the internet. So as long as you know the temperature data and you know when and what you planted, you can sort of back out what the current growth stage must be. And actually, it works pretty well. So if you know how many GDDs you've accumulated so far, you can get a good estimate, maybe within a stage or two, of what the growth stage in practice is. And when you get up to the reproductive phase, it is even better. It's almost a perfect match in this particular case. And so when you're planting seeds, and it turns out that it's so useful, this GDU number, that your seed manufacturer has measured 2 points. The number of GDUs to the black layer. So in this particular case, it's 2,850 GDUs to get to black layer. So once you plant it, and however long it takes to accumulate 2,850 GDUs, that's when the plant will finish and black layer will form, roughly. And also this growing degree units pollination, that's essentially to the point of silking. And so there's 1,377 GDUs needed to get to the silking stage. Similarly, say for Pioneer, you can go to their website and put in a particular variety name, and get the same sort of numbers. 1,380 to silking, 2,600 to maturity. So if you know what you planted and where you planted it and when you planted it, you can consult your temperature sources and use your manufacturer's variety information to estimate field stages. And now you can essentially estimate the growth stage of all your fields in the farm every day with almost no effort. So before we sort of really get into that, let's better define what we mean by GDU, just so we're all on the same page. And it's really essentially this really rough measure of, I'll call it, growth energy. It's like how much energy was the plant given to turn into mass. It's like I mentioned before, called growing degree unit. Sometimes it's called growing degree day, or sometimes it's just referred to as heat units. They're all the same thing, and it's defined to be just the average number of degrees that the plant experienced in one day. So the units of a GDU is the number of degrees times day. And so we can just write T high plus T low over 2. That's the average temperature for a given day. But when people really looked at this, they noticed that when the temperature is below a certain value, the plant doesn't appreciably grow. So there's sort of like a minimum. You have to have a certain base temperature and more to accumulate growth. And so we can adjust our formula now to account for that just by subtracting off that base temperature, which is usually taken to be 50 degrees Fahrenheit for corn, from the average temperature. And that sort of tells you how many growing degree days above your base temperature that the plant received in that day. Also turns out that there's a temperature that if you go over it, it doesn't really grow any faster. In a sense, there's a temperature which makes the plant achieve its fastest possible growth rate, and any temperature over that can't make it go any faster. In fact, any temperature over that might actually slow it down because of heat stress, but that's a different issue. Actually, dealing with this maximum temperature is kind of messy, and we'll see how we handle it in a little bit. For now, we're going to ignore it. But you might be asking yourself, like, why the average temperature? Where did that come from? And it comes from thinking about like what a typical day is and what does it mean by energy. And so if we have a day that looks like this, where it's kind of a sinusoidal pattern, so sometime we have a low, and then in about midday we have our high, and then we go back down to our low, and sort of kind of a smooth curve, then the energy available in that day, or sort of heat energy, is sort of somehow related to the area underneath this curve. Now, a real day probably doesn't fit this model perfectly. Real days probably have a high that's more like late afternoon and have lows that are more like early morning hours, right? And in fact, if we look at this curve right here, which is a curve from right in the middle of the season of this year, you can see it does kind of have a sinusoidal nature, and right around 6 a.m. is our low, and right around 5 or 6 p.m. is our high. So it is shifted like we mentioned. Well, it turns out if I take this sinusoidal form here and I kind of shift it left or right however I want, it doesn't change the area underneath the curve. So this sort of like shift doesn't matter too much. And so I'll just draw it the way we have it here because it makes the math a little bit easier to work through. But it should be worth noting that GDUs have a lot of practical issues. A lot of assumptions that don't map to reality very well. And one of them is, say, that a day is sinusoidal in nature. So here's the very next day. It has a little bit of a sinusoidal nature. It kind of goes from a low to a high to a low, but not really nice and neat like the ideal model. And then the next day after that, it's actually basically flat. And in fact, the low happens in the afternoon and the high happens in the morning. Now, of course, what's happening here is just weather patterns, right? Maybe a cold front blew through. So we had a nice sinusoidal day, and then as that cold front comes through, the temperatures actually ended up getting colder later in the day because of that pressure system, and not because of the natural cycle of the day's temperatures. And so it doesn't really fit the mold very well. It turns out GDUs work really well, even with all these problems. So we're going to ignore it and just look at our ideal model. That's where the equation comes from. And then we're going to apply it and see how well it works. So to kind of figure out the area under the curve, we basically need to do an integration. Now we're not interested in any of the energy below T base because the plant doesn't grow there. We're just interested in the energy from T base up to the temperature at the given moment in time. And so to get that area, we do this integral that looks something like this. And we could compute the integral. In fact, it's really not a very complicated one to compute, but we can do it even a simpler way if we break it up into two parts. If we look at just the area underneath this sinusoid waveform here, then we have our well-known result that the area of a sinusoid with an offset equal to its amplitude is equal to just the amplitude times the length. The amplitude here being from the distance from here to here. So from T high to T low over 2, that's its amplitude, and then times 1 day, because this sinusoid goes 24 hours, or 1 full day. Then we can take the area of the rectangle below it. We know the area of the rectangle is just height times length. Height here, again, is from T low to T base, so we subtract them, and our length is 1 day again, so times 1 day. And now if we want the area under the whole thing, we can just add the two areas that we computed separately together. And then we do a little bit of simplification, and we get to this equation that says GDU is T high plus T low over 2 minus T base, which is the equation, or times 1 day, which is the equation that we saw earlier before. Now we'd oftentimes drop this times 1 day part because timesing a number by 1 doesn't really change the number, but it's important from a unit consideration. This stuff in the parentheses has a unit of degrees, and this has a unit of day, which gives us our total unit of degree days, and therefore why we call it growing degree days. Now there's some issues. For example, what happens if T average is less than T base? So in this case, if T average is less than T base, then this will be negative, and we have negative GDUs. But we know that just because it's cold, the plant doesn't shrink, doesn't grow backwards, right? Well, it turns out this is pretty rare. It's not going to happen very often. It's probably only going to happen very early in the season when it's still kind of chilly out. And we just call those negative days 0. And that's just sort of a heuristic that we do, and it's how everyone applies them. And it really doesn't have any large impact on it. It's not a problem in practice. The other issue is when our high temperature of the day is over the maximum temperature that the plant has. Maximum meaning that's the temperature which the rate of growth is at its maximum. And how we deal with that is we just replace the high temperature with the maximum temperature. And in a sense, what we're doing is integrating this red curve, where we've allowed the sinusoid to be what it wanted to be on the lows, but we made the high just equal to the maximum. And when you compare that to the energy that we actually wanted to compute, what we really wanted was this yellow curve here that follows the sinusoid all the way to T max, then is flat, and then follows the sinusoid down. So this sort of yellow region here and here, we're undercounting, we're missing by integrating underneath this red curve. Well, it turns out it's just a lot easier to integrate under the red curve than it is to integrate under this sort of clipped sinusoid curve. And so we just use the red curve in practice. It's not a very big energy, it's not a very big area that we're missing. Turns out that it's really not a big problem in practice again. And so you might be thinking to yourself, man, this GDU thing is kind of rough. Just to explain it, I've had to make several assumptions. I've had to hand wave a few things, and I've had to say, oh, don't worry about it. In practice, it works. And it's because GDU is a heuristic, right? We need to make sure that we understand that. It's not a scientific model. It's not some fundamental element of how the plant grows. It's a heuristic that we've come up with to show a relationship between it and growth. And it turns out it's fairly predictable. We saw the plot earlier. I'll show you some data at the end of the slides too, that it works. Even though it's kind of messy, it's kind of funny sometimes how the more complicated, more detailed models can miss the mark because they can get confused by the noise of the process variation, where the sort of simpler kind of rough models like the GDU can often work really well because they tend to average out some of those process variations. There's a couple other things to consider here. Even though it's not perfect, but it works fairly well, it's also really easy to compute. We have weather data, specifically historic weather data that only has min and max temperatures. Recording hourly weather data is sort of a somewhat modern invention. When we started doing automated weather stations, it became a lot more common. Now, even back in the day, before automated weather stations, we still had weather stations that did report hourly data, but they didn't all report hourly data. So to have the heuristic require only min and max temperatures really expands the amount of historical data that we can train a model on. Also, the heuristic is, at least as defined, is really easy to compute. So from computationally perspective, it's a really nice feature. The other thing to consider is that all those errors and inaccuracies in the heuristic are probably overwhelmed by other things like process variation and just the growth. How much sunlight was there? How much water was available? How much nutrients were available? Gene factors, soil temperature versus air temperature is important. What stresses were present or not present? These types of things change the growth rate just as much as the GDUs do. And so even though we have some slop in the GDU, there's other slop that we're not accounting for either. And what matters is that essentially in practice, it seems to work. It's been proven over and over and over again. It's been used for a long time. And so we're going to use it for our app as well. So hopefully I've kind of convinced you that GDUs are a useful thing and that you should start using a tool to manage or to track GDUs to help you make decisions. There are a lot of them out there. Like, this is just the beginning of a long list. And they all tend to do the same sort of thing. This right here is a picture of the useful to usable corn GDU tool out of the MRCC. And essentially you put in your plant date, you put in your black layer and your silking numbers, and then it uses a free public data source for weather, the ACIS from the Regional Climate Center, which is actually the same weather data that our Grow app will use. And it makes these plots that shows you the GDU accumulations over time from the beginning of your plant date, and then it'll show you what days that on average you would accumulate enough GDUs based on, say, 20 or 30 years of historical data. This is a useful tool, but it's not, it doesn't solve all the problems. And you might ask yourself, well, why are we building our own tool? In fact, Purdue already has some GDD tools. Why are we building a new one? Why Grow? And it's based on the idea that growth stage is one of those pieces of contextual information that you need as a grower to make a good decision, not necessarily GDU. And the tools that exist around GDUs right now make it difficult to go from GDU to growth stage estimation. And there's a couple of reasons, but the primary ones are that most of these tools don't have any mechanism to remember where you planted, what you planted, and on what day you planted. So you have to re-enter that data for every field every time you want to use it. It's really almost no easier than just scouting yourself. And the other problem is that a lot of times these tools aren't free. Or the ones that do know your field locations and your planting dates and things like that, they're the ones that aren't free. And so it's fine if you're a customer of that product, because then you can just use the tool. But if you're not a customer of that product, then you don't have access to this sort of useful auto estimation. So we set out to build an open source web and mobile app that can quickly and easily indicate the growth stage of your entire farm all at once using nothing but public data sources and no backend at all. So essentially, we could all retire tomorrow and the app would continue working for you. And this is a prototype right here. And you can see we had a map view and here's a list view. It comes with the default field. Here I'm adding a shapefile. The shapefile is uploaded. It doesn't go to a backend. It's processed entirely on your phone by the app. All the fields are imported and saved. So the next time you open the app, your fields are there. Then we can go back to our map view and see our whole farm sort of geospatially. Like I said, this is all free and open source. It's web-based. It's a progressive web app, which means you can install the web app as a native app on Android and iOS. So it supports all the major platforms. All your data is stored on your device, not on our back end. Now we are planning on adding a Google Sheets feature where your data would be stored to your Google Sheets. So that way, if you have multiple devices, you don't have to keep uploading your shapefile and your planting information. You just do it once, it syncs to Google Sheets, then all your other devices can sync that data down from Google Sheets. But we don't have access to that data. That lives entirely in your Google account. And like I said, it can automatically recall your fields and planting data. Every time you open the app, it just knows it and can show you the most up-to-date data. You don't have to keep re-entering that information. So taking a little bit closer look into the app, you can see that in the kind of list view here, we have the name of the field, we have the date that we planted the field, and the variety. And this was information you had to enter by hand. You would do that by clicking this little edit button. You'd only have to do it once, but we would need that to be able to drive the rest of the app. Then the app predicts the finish date based on that variety information and the historical weather data for that field, going back, say, 20 or 30 years or so, depending on the specific field. It'll also tell you what it thinks its current estimated stage is. So in this case, this is V18. This is on July 13th of this year. And this is real planting data on a real farm. And it was saying that in 3 days later, it would be V19. And it also tells us how much rain we've had in the last day, in the last 3 days. So with that, you can imagine making some logistical decisions based on it. For example, maybe you only had time to scout 2 fields today. And so you need to ask yourself, well, which fields should I scout for? And like one of the things you could do is check for the fields that are most likely to have a disease that you want to eradicate or a pest that may be a problem. So you can come here and sort this list by the stage that you're interested in and see which fields are the most interesting ones to go scout, that are most useful of your time. Or maybe you were side dressing and it rained for a while and it's been about a week since you've been able to get out in the field. Now you need to know which fields should you go run on. You could use this tool to find the fields that are still within the acceptable product range, label range, right? So maybe some of those fields have progressed too far in that week at this point and you can't get out there anymore. But once you figure out which fields are acceptable to go run on, you might want to then sort them by the largest stage to the smallest stage so that you attempt to make sure that none of the crops get too tall and you can still run over them. So there are a lot of decisions like this that you can make that affect sort of day-to-day logistics of the farm, and you can make better decisions than you make today if you knew the current growth stage of all your fields at any given day. So you might be asking, well, where can you get the app? Well, just like any nice car rebuild, we are carefully assembling all the pieces, and unfortunately, I'm not quite done doing it yet. The intention was to get an app released for today, but it's not quite ready, and so instead of releasing a buggy thing, I'm going to go ahead and keep working on it and do a beta release here in the next week or two. So essentially, we have the nice looking car right now, but it has no engine, and I still need to put the engine in it. I would say make sure you check our Digital Ag Resources website. Maybe we'll get a link posted in the chat here in a few minutes. That's probably where we'll announce the beta release. And if you have a chance, I really encourage you to install that beta release and play with it. Any real feedback, feature requests, some decisions you think you would make if the app could just show you, this certain piece of data, it'd be really great to know. I can make up features all day long, but unless they're solving a real problem for you, it won't be useful for anybody. So it's really great feedback for me. And then we're planning on having sort of version 1.0 ready for the 2021 planting season. Again, watch the Digital Ag Resources website to hear about the update. So with that, I'll stop and leave it to any questions that you may have. And thank you very much for listening.